32 earthquakes hit one small piece of Northern California in a single day this week. Over 7 days, the count reached about 80. The largest was a magnitude 4.2. All of them are shallow. All of them are 75 miles from San Francisco, and the sequence is spreading in a direction that matches no mapped fault in the area. Seismologists have seen this on this exact fault before. By the end of this, you will know what it was, and the one number that would change everything. There's a patch of hill country in northern Sonoma County, California, about 8 kilometers east-southeast of the town of Cloverdale, that has produced roughly 80 earthquakes in the last 7 days. 32 of them arrived inside a single 24-hour window ending Saturday. The largest of the week was a magnitude 4.2. A magnitude 3.8 struck just after midnight on Saturday morning, and the entire sequence is happening at a depth of about 2 to 3 miles below the surface, with some events shallower than that. To put the location in terms that matter, this is roughly 75 miles north of San Francisco. It is in wine country, off Highway 101, in terrain where the nearest town has a population of about 9,000 people. Cloverdale itself has felt a lot of this, so has a good stretch of Sonoma and Mendocino counties. None of these earthquakes has caused significant damage. A magnitude 4.2 is a solid jolt, not a disaster. A magnitude 3.8 rattles dishes. If you judge this sequence purely by the numbers on the individual events, you would file it under routine Northern California seismicity and move on. It is also worth understanding what the word swarm actually means here, because it is not a synonym for a lot of earthquakes. A normal earthquake sequence has a shape. One event dominates the main shock, and everything that follows is smaller, arrives afterward, and tapers off along a predictable decay curve that seismologists have been fitting to data since the 1890s. You can watch it happen in real time on any large quake. The big one lands, the aftershocks pile up in the first hours, and the rate drops off steadily from there. A swarm has no such shape. There is no dominant event, no clean decay, and no obvious start point. Energy is distributed across dozens or hundreds of similar-sized earthquakes over days or weeks, and the sequence can go quiet for a day, and then re-intensify for no visible reason. That behavior points at a different driver, not a single locked patch of fault snapping and then settling, but something moving through the rock and switching structures on one after another. That is not what the people watching this catalog in real time are doing. They are watching it very closely, and the reason has nothing to do with the size of the earthquakes. It has to do with the direction they are moving. The faults in this part of California all point the same way. They are part of the San Andreas system, and they share its orientation, running roughly northwest to southeast, which on a map reads as more or less north to south. The Maacama fault, which is the structure this swarm sits on or right next to, is a right lateral strike-slip fault with exactly that trend. It runs north from Santa Rosa, past Ukiah, and it forms the northern continuation of the Hayward and Rogers Creek fault system. When a strike-slip fault produces an ordinary aftershock sequence, the earthquakes line up along the fault. They form an elongated cloud that traces the plane that broke. That is not a rule of thumb. That is what a fault rupture is. The earthquakes mark the edges of the patch that slipped. The Cloverdale sequence is not doing that. It is spreading west to east. It is running across the grain of every mapped structure in the area, at a high angle to the faults it is supposedly occurring on. The phrase being used by people tracking the catalog hour by hour is that it is spread out in an abnormal fashion and running opposite of what the faults run. And the conclusion they have drawn from that is blunt. This is not an aftershock sequence. They are right about the observation. The geometry is genuinely strange, and it is the single most important fact in this entire story. But there is a published explanation for exactly this behavior, on exactly this fault, and we will get to it, because it is both more interesting and considerably more grounded than the alternatives circulating online right now. First, though, it is worth being honest about what we actually know about the fault this is happening on. The Maacama fault moves at about 9 millimeters per year. That is roughly 1/3 of an inch annually, a meaningful rate for a California fault, comparable to some of the better-known structures in the Bay Area. Parts of it also creep, sliding along aseismically at something like 7 millimeters per year without producing earthquakes at all. That creep number deserves a moment because it changes how you should read everything else. A fault that creeps is a fault that is partially releasing its stress continuously without earthquakes. The two sides slide past each other slowly enough that you can watch it deform a curb or a fence line over decades. Faults that creep along their entire length are generally considered less dangerous because the strain never accumulates to the point where it has to be released violently. Faults that creep in some places and lock in others are a different problem. The locked patches keep loading while the creeping sections quietly slide, and the boundary between the two is where things break. On the Maacama, we know creep is happening. We do not have a good map of where it stops. Here's the part that should get your attention. Scientists know remarkably little about the Maacama Fault's earthquake history. Its paleoseismic record, the trenching work and sediment analysis that tells researchers how often a fault has produced large earthquakes in the past, is thin. Its earthquake cycle is poorly constrained. Nobody can tell you with confidence how often this fault produces a major event because nobody has been able to establish the pattern. That matters because the Maacama is not an isolated structure. Follow it south, and it connects to the Rogers Creek Fault. Follow Rogers Creek south, and it runs under San Pablo Bay, where researchers verified that it links directly to the Hayward Fault. The two are now mapped as one continuous structure rather than two separate faults. So the thing shaking under Cloverdale this week sits at the northern end of a chain that runs down into the most heavily populated part of Northern California. That is not a prediction. The Maacama producing 80 small earthquakes does not mean the Hayward Fault is about to do anything. Faults in a system are not dominoes, and treating them that way is how people talk themselves into forecasts that never arrive. But the structural connection is real. It is mapped, and it is the reason this particular fault gets more attention than its size alone would justify. In August of 2020, an earthquake sequence started inside the Maacama fault zone. It reached a maximum magnitude of 4.2. It generally decayed over time, but it kept restarting, persisting episodically all the way into December of that year. And when seismologists first looked at it, it appeared exactly as strange as the current sequence appears now. 3 researchers, Shelley, Scummel, and Hardebeck, spent the following years taking that sequence apart. They published the result in Geophysical Research Letters in 2023, under a title that gives away the answer, Fracture Mesh Faulting in the Swarm-like 2020 Maacama Sequence. What they did was brute force precision work. They used waveform correlation to detect earthquakes far too small to appear in the standard catalog, then relocated them relative to one another, then calculated high-precision focal mechanisms, the solutions that tell you the orientation of the fault plane that produced each event. They ended up with 3,520 relocated earthquakes, most of them below magnitude 1. Earthquakes that nobody standing on the ground above them would ever have felt. The reason that method matters is that the small earthquakes carry the information. A standard regional catalog might record a few hundred events from a sequence like this, everything above roughly magnitude 1.5, located to within a kilometer or so. That is enough to tell you where the sequence is, and almost nothing about its structure. Push the detection threshold down below magnitude 1 and relocate everything relative to everything else, and the smear resolves into individual planes. You stop seeing a cloud and start seeing the actual faults. 3,520 events is the difference between knowing something happened and knowing what happened. And what that catalog showed was this. The sequence did start on a right lateral fault, plausibly a strand of the Maacama itself, behaving the way the Maacama is supposed to behave. But it did not stay there. It activated a whole population of secondary faults running the other way, left lateral structures, arranged in an overlapping stepped pattern, cutting across the parent fault at an angle. Together, the main strand and all those cross-cutting secondary faults form what the authors called a fracture mesh, not one plane. A 3-dimensional interlocking network of small faults, all of them capable of slipping, all of them oriented differently from one another. That is why the geometry looks wrong. A fracture mesh does not produce an elongated cloud along the main fault, because the earthquakes are not happening on the main fault. They are happening on the cross structures, which by definition intersect the regional grain at a high angle. A sequence spreading west to east across a north-south fault system is not behaving impossibly. It is behaving exactly like a fracture mesh, a thing this specific fault zone demonstrably produced 6 years ago at the same maximum magnitude of 4.2. The second half of that finding is the part that explains why this is happening at all. Fracture meshes are associated with fluids. The authors state it directly. These interlocking structures match what has been found elsewhere in cases of fluid-induced faulting and earthquake swarms. The mechanism is straightforward once you see it. Rock under pressure at depth is held closed by the weight of everything above it. Push pressurized fluid into that rock, and you reduce the effective stress clamping the faults shut. Faults that were locked become slippable, and because the fluid is moving through a damaged volume of rock rather than along a single clean plane, you get many small earthquakes on many small structures over days and weeks, instead of one large earthquake on one large structure in a few seconds. That is the textbook definition of a swarm, and it fits what we are seeing. No main shock. A magnitude 4.2 leading a population of 80 rather than a magnitude 5, with everything decaying away from it. A sequence that has persisted for a week and re-intensified rather than fading. And the largest event of Saturday's 24-hour window, at magnitude 3.8 after midnight, arriving on day 6, which is not how aftershock decay works. The regional setting supports it too. This part of California sits near the Clear Lake volcanic field, inside the broader thermal province that hosts the geysers, the largest geothermal electricity complex in the world. The crust here is warm, chemically active, and structurally beaten up. It is exactly the environment that supplies circulating fluids at depth. To be clear about one thing, because it comes up every time, the swarm epicenters are in a separate area from the geothermal production field. This is not an induced seismicity story. This is regional geology, natural fluids and naturally fractured rock, in a place that has been doing this on its own for a very long time. And here is the honest caveat, which matters more than any of the above. The 2020 analysis took years of high-precision post-processing on thousands of relocated microearthquakes. Nobody has done that work on the current sequence. Because the current sequence is 6 days old, fracture mesh is the best supported explanation available right now. It is not a finding. It is the hypothesis that fits, held loosely until somebody does the math. This swarm did not appear out of nowhere, and that context changes how you should read it. On June 24th of this year, a magnitude 5.6 struck near Ukiah on the same fault system. That was the largest earthquake ever instrumentally recorded on the Maacama. Not the largest in a decade, the largest since instruments had been watching it. That June event deserves more weight than it got at the time. When a fault produces the largest earthquake in its instrumental record, the honest reading is not that the fault has become more dangerous. It is that our record is short. Instruments have been watching the Maacama for a few decades. The fault has been moving for millions of years. A record-setting magnitude 5.6 on a structure like that tells you far more about the length of the observation window than about the state of the fault. But it does establish something useful. This system is capable of producing events in the mid-5 range, and it did so 6 weeks ago, 40 miles north of where the current swarm is. Then, on July 28th, a magnitude 4.3 hit near Cloverdale at 20 to 8 in the evening, Pacific time, at a depth of about 5.5 kilometers. The U.S. Geological Survey flagged it as a potential main shock, and the sequence that followed ran to more than 160 events. Now we have this week, 80 more earthquakes, a magnitude 4.2, and a geometry that does not match the fault. So the correct framing is not that a swarm started last week. The correct framing is that the Maacama fault system has been switching on and off for 6 weeks, escalating in complexity, and it has not stopped. Whatever is driving it, and the fluid explanation is the strongest candidate, it has been driving it since late June. That is the primary story. What follows is context, and it is the reason a lot of people started looking at Northern California in the first place. On Friday night, at 49 minutes past 9 Pacific time, which is 4:49 in the morning Universal Time on Saturday, a magnitude 5.6 earthquake struck beneath the ocean floor west of Vancouver Island, British Columbia. The depth was about 10 kilometers. The coordinates put it at roughly 49.6 degrees north, 129.3 degrees west. Light to moderate shaking was felt on Vancouver Island, and reports came in from as far south as Washington State. No damage. No tsunami threat from any agency. And as of Saturday afternoon, more than 12 hours later, not a single aftershock had been cataloged from it. That last detail is worth flagging. Part of it is simply detection. An earthquake below about magnitude 4.5, 200 kilometers offshore, will not register on land-based instruments at all. But a genuinely quiet interval after magnitude 5.6 on an oceanic fault is still a data point, and it is the opposite of what the Cloverdale sequence is doing. Now here is the detail that made people pay attention. This was the second magnitude, 5.6, on that exact structure in 12 days. An identical magnitude event struck the same region on July 20th, located by Earthquakes Canada, about 219 kilometers southwest of Port Hardy, at essentially the same depth. It carried a green alert, no tsunami risk, and was felt as far as Metro Vancouver, more than 450 kilometers away. 2 earthquakes, same magnitude, same depth, same structure, 12 days apart. To understand why that repeat is not surprising, you need to know what is actually up there. What most people call the Juan de Fuca plate is 3 plates. The Gorda plate sits at the southern end, offshore Northern California. The Juan de Fuca plate proper is the large middle section. And the Explorer plate is the small fragment at the far northern end, west of northern Vancouver Island. The Explorer plate is being torn off. It is fragmenting along its boundary with the Juan de Fuca plate, and the working interpretation among researchers is that it is progressively decoupling from the subduction process entirely, that on geological timescales it may stop subducting and convert to a sliding transform boundary instead. That is not speculation from a comet section. A 2025 study in Science Advances, led by Brandon Shuck, imaged it directly. Using seismic data collected aboard the research vessel Marcus G. Langseth, the team found 2 active tears in the subducting slab and a fault network roughly 20 kilometers wide, cutting through sediment, through crust, and into the upper mantle. The Explorer microplate is in the process of being severed from the system. Both of these magnitude 5.6 earthquakes happened inside that structure. And that gives us the single most important interpretive line in this segment. These are fracture earthquakes on a plate that is coming apart. They are not megathrust earthquakes on the Cascadia interface. They tell us that the northern end of the system is disintegrating on schedule. They tell us nothing whatsoever about when the locked zone will fail. There is one more thing about Friday night worth 2 minutes, because it generates more suspicion than almost anything else in this field. For 20 to 30 minutes after that earthquake happened, the U.S. Geological Survey feed showed nothing at all. The European Mediterranean Seismological Center published first, near magnitude 5.6, carrying its standard note that the parameters had not yet been reviewed by a seismologist. Earthquakes Canada, the national agency responsible for that region, initially did not have it on the map, then posted it at 5.0. The European Center then revised down to 5.3. And roughly half an hour after it happened, the U.S. Geological Survey finally published at 5.6. Canada eventually settled at 5.5. So the public watched a magnitude walk from 5.6 to 5.0 to 5.3 and back to 5.6 across 3 agencies in half an hour. The explanation is geometry, and it is boring in the best possible way. An earthquake 200 kilometers offshore has no instruments on the seaward side of it. Every station that records it is on land, on one side. That one-sided coverage produces a badly constrained solution. Depth in particular often is not measured at all. It gets assigned a default value, and 10 kilometers is the classic default you will see over and over on offshore events. The magnitude estimate then swings as more distant stations report in, and the automated algorithms resolve. 3 agencies, 3 algorithms, 3 different station networks, 3 different subsets of the arriving data, and no human analyst yet. Of course they disagreed. The fact that they all converged within half an hour is the system working correctly, not the system hiding something. There is a third thing happening on this coastline right now, and it is the one that actually connects the north end to the south end. Cascadia produces slow earthquakes. Underneath the locked portion of the megathrust, the part that will eventually produce a magnitude 9, the plate interface slides slowly and quietly over days and weeks rather than seconds. Seismologists track it as tremor, and tremor is not a countdown clock, it is a stress gauge. When tremor is running, the slab is being actively shoved beneath North America, and stress is being transferred onto the locked zone above it. The mechanism is worth one more sentence because it is genuinely unusual. Down at the depths where tremor happens, the rock is hot enough that it does not snap. It deforms. So instead of storing stress until a fault fails all at once, the interface releases it in slow pulses that last for weeks and produce a faint, continuous rumble rather than a sharp jolt. Nobody feels these. They were only discovered in the early 2000s, when researchers realized that the noise they had been filtering out of their data was a signal, and every one of those slow pulses hands its stress upward to the shallower part of the fault that is still locked and still capable of snapping. Through mid-July, tremor was running hard. 307 epicenters were logged on July 14th across the full margin. By July 24th, the tally had climbed to 382, with the concentration shifting to the southern end, offshore Northern California and Southern Oregon. Then it stopped. There was activity beneath Northern California and the Oregon Valley around July 25th, and from roughly July 27th onward, effectively nothing. A single cluster of about 40 epicenters beneath southeastern Washington on Saturday, and 3 to 4 days of near silence before it. Now hold that against the primary story. The stated working relationship on this margin is that elevated tremor comes with what get called stress quakes in Northern California. The slab loading up, the strain expressing itself down the coast. Tremor is currently at its quietest in weeks, and Northern California is producing a swarm anyway. That brings us to the claim circulating online, which is that all of this together represents the West Coast unzipping, one connected failure propagating down the plate boundary toward a major California earthquake. The data does not support it, and the reasons are specific. Static stress transfer, the permanent stress change caused by one fault slipping, falls off roughly as the cube of the distance from the source. The Vancouver Island epicenter is about 1,100 kilometers from Cloverdale. At that range, a magnitude 5.6 produces a stress change smaller than what a passing weather system delivers. Dynamic triggering, the transient stress carried by seismic waves, is real and has been documented at continental distances, but it is associated with much larger earthquakes, generally magnitude 7 and above, arriving at sites already on the edge of failure. And the decisive fact is chronological. The Cloverdale sequence was already running for several days before the Vancouver Island earthquake happened. The swarm did not start after the quake. It was already there. 3 unusual things are happening on the same coastline. That is not the same as one thing happening in 3 places. So here is what actually matters going forward. On the Maacama, the thing to watch is not whether the swarm continues. Swarms continue. That is what makes them swarms. The thing to watch is whether the maximum magnitude climbs. The 2020 sequence topped out at 4.2 and stayed there for 4 months. This one is currently at 4.2. If the ceiling holds, the fracture mesh interpretation gets stronger, and this is a fluid story that will run its course and stop. If a 5 appears, the interpretation changes, because that starts to look like a single structure taking over from the mesh. Watch the ceiling, not the count. Watch the footprint as well. If the sequence keeps spreading east to west across the grain, that is consistent with a mesh illuminating cross faults. If it suddenly organizes into a line along the Maacama trend, something different is happening. At the northern end, expect more fracture earthquakes off Vancouver Island. A plate that is actively tearing apart produces earthquakes while it tears. A third magnitude 5 in that same fracture boundary would not be a surprise and would not be a signal about Cascadia. It would be the explorer plate continuing to do the thing it has been doing. And on the interface itself, the number to watch is the tremor count. When the next slow slip episode begins, and it will, these run on cycles of roughly 10 to 22 months depending on the segment. That is when stress starts loading the locked zone again. 326 years have passed since Cascadia last ruptured on the 26th of January, 1700. Quiet does not mean the pressure has come off. It means the slab is between episodes. The single most useful thing in all of this is the least dramatic. A fault 75 miles north of San Francisco, one that scientists openly admit they do not understand well, has spent 6 weeks producing sequences that do not fit the standard model. That is not a warning of anything imminent. It is a reminder that a structure connected to the Hayward Fault is being studied in real time by people who are candid about the limits of what they know. We will be tracking it as the week develops.